Okay, well, thank you very much, ladies and gentlemen, for coming, and thank you for accepting me into this session. So I'm very pleased to provide you a summary of a study that's being undertaken in Western Canada. I think it's one of the most monitored landslide sites in Canada. I'll give you a brief overview of what's actually being undertaken. There's a list of my colleagues from a number of institutes listed at the bottom, which have contributed significantly to this. First of all, the site in question is related to the national railway system. As you can imagine, Canada is an extremely large country. It has very diverse physiography, geology, extreme climatic conditions from one end to the other. And the rail infrastructure is extremely important for shipping of goods, not for human transport, but for goods. The next map here shows the distribution of the two primary rail systems. They also run into the States, but if you look in Canada, it extends from one coast to the other, primarily along the southern borders. The area of concern, of course, is the West Coast. What we try to do is bring goods either from the coast into the interior of Canada or from the interior of Canada to the coast. And you can see on the west side of Canada, there's only two locations at Prince Rupert and Vancouver where this is possible. So I've circled here in red the area of concern for this particular study. If we zoom into that area, what you can see is, first of all, I've circled in yellow the Port of Vancouver, where both rail systems end up. One rail system, is that gone up? Yeah, one rail system here, the CPR, comes in directly from the east and eventually meets up with the other rail system, the CNR, in an area near Ashcroft. So you can imagine there's a mutual working relationship between these two rail companies. If something happens to a rail track for one company, they can easily start moving goods on the other. That works very well through most of Canada until you reach the area of Ashcroft right there. And through that whole corridor, the two rail systems run parallel to each other. So if a landslide affects the rail system, it likely affects both rail systems at once. And that would essentially cut off transportation from or to the Port of Vancouver. The importance of this section, of course, is how much a rail actually goes through. It moves all kinds of goods. Besides the rail system, there's power transmission lines, highways, etc. running through this corridor. But there are approximately 80 trains that run over a 24-hour period, 3 to 4 trains per day or per hour, some as long as 4 kilometers in length. So you can imagine any disruption in rail traffic to begin to cost tens to hundreds of millions of dollars depending on the length of shutdown. So this area is extremely important. Along this corridor, now if we zoom in, Ashcroft is to the north, and you can see we're showing a small stretch of the Thompson Highway. There are a number of types of landslides. Historically, there's just over about a dozen landslides, and notice that they're all within the last few centuries, fairly large scale. Those are all the yellow dots. The name of the slide is given, and in brackets the year of the event. Our particular slide is called the Ripley slide. It's shown in red. And there are basically 4 types of slides: slow-moving, fast-moving, and either translational or rotational in nature. I'll give you an example of one particular type of slide. Here, this is a fast-flowing slide that occurred or rapid flow slide that occurred in 1880. And you can see the size of this. It's extremely large, and this is the rail track that goes here. So the railway is actually built across the toe of this particular failure. Our slide, however, isn't this type of slide at all. It's not a large catastrophic flow or slide at all. I'll get to that right away. This is a DEM of where we're located. You can see it's actually fairly moderate relief. The track system runs along the bottom. Our slide is down here. Some high relief farther up into the mountain areas, but generally a moderate sloped area. This is a photo of the slide. It became active in about 1950. As I said, it's about 400,000 cubic meters, and it's slow moving. So it's unique in comparison to the other dozen slides, but it's a nuisance to the rail systems. Note that both tracks, the company called CPR and the other company CNR, are at the base of this failure. The movement ranges from a few millimeters to several tens of millimeters per year. I'll give you the numbers right away. And what this requires is for the rail companies now have to come in virtually 6 times a year to start adjusting the track. Because rail tracks, unlike roads, have to be maintained at a particular a level of quality. So it's quite costly for the rail company to come in every 2 months and try to fix this slow-moving creep. So we've decided to start monitoring this feature in cooperation with both rail companies, University of Alberta, and the Geological Survey of China. Here's an example of some tension cracks near the headscarp. So you can see these are just progressively growing. And this is the list or suite of field study and monitoring that we've initiated at the site. And in the brief time that I have here at this conference, I'm just going to briefly give you a summary of some of these at the site. Well, first of all, we're in an isolated area of Canada, as I noted, but we're fortunate enough to be working with CNCP. So they've installed this bungalow or storage shed so that we can actually have equipment in place, provide power to the area, both ground power as well as solar. We've got radio telecommunications here as well to transmit the data remotely. We can access this from basically anywhere in the world through FTP sites. And it's protected relatively from the elements, the storage shelter, except for one particular hazard, which I'll discuss at the very end of this presentation. One of the initial monitoring at the site, besides the observation of ground deformation, the rail companies put in these GPS monitors, these permanent stations, one located here, one here, and a third one. And the amount of movement that's been recognized at this end, the north end of the slide, as little as 2.5 millimeters per year. This station here up front, GPS station 2, up to 36 millimeters. And the last station I'll show you, located between the two rail tracks, moves as much as 55 millimeters a year. And that's quite significant, as I said, in terms of reparative costs. This is the third station here. So there's a track that's right here and another one right there. So this is located right in the middle where the biggest problem area is. We started by mapping the superficial geology of the area. There are also all the instrumentation is shown on this particular map. It's basically glacial sediments, glacial lacustrine, till features such as this, or deposits such as this, that cover this particular site. As I said, we've cooperated with the private sector and the CP and CN Rail. These are colleagues from the University of Alberta that are doing LiDAR, generating DEMs, doing the interferometry, as well as ground-based and INSAR. And there's also been some borehole work done, also extremely expensive to get into these locations because we're so far away from civilization. So we haven't done very much borehole, but we're sampling and doing standard analyses on these samples. The cores coming out, they're down to a depth of about 40 meters. At certain areas we can see slick inside at the contacts. And then the instrumentation. Again, we've got, in this particular case, we've got piezometers in place. We have the corner reflector, 1 out of 9 for satellite imagery. We have getting power, essentially solar power. We've got 2 piezometers as well as a shape accelerate. If you're not familiar with that, it's much like an inclinometer, except it's very flexible. We'd installed inclinometers in there, but within a year they're sheared off, so it's of absolute no use. And the shape accelerate is like a garden hose. What it allows you to do, you stick it in, it's continuously monitoring, but it allows almost full curvature, so it doesn't matter how much deformation you get in the side, you're still recording things. So this technology has proved to be extremely useful. This is a imagery of the INSAR that we've put in. We've got 9 of these corner reflectors placed across the site. This is being analyzed by Hengxin Liu from China. This is his plot or land. So what I'll show you here is these 2 corner reflectors here are on stable portions of the territory. So we're using these as ground-based reference points. The rest, the red part, you can see the entire mass is moving a bit. And then the maximum amount of movement is in the southern end of the site. So because of this, we also did some shallow geophysics. And we put in 5 transects using these 4 methods. These are the transect lines we did. I'm going to quickly show you some north-south transects and then the east-west. And the problem area is right there. So first of all, the north-south transects, you can see it ranges from a few meters to several tens of meters. The blue area is primarily clays, glacial lacustrine clays, and then the red is the bedrock, resistive bedrock. So that's north-south. This is the southern area of the slide, and we can see that there's a bit of an anomaly there. And then east-west transects going from uphill to downhill. And the area of concern here in black, we've now discovered that there's a large detached chunk of bedrock that's been incorporated into the subsurface sediments that's causing the maximum amount of movement. So this is going to be our primary area of focus because this southern end is where the maximum amount of movement is actually being undertaken. Here's a view of the southern end of the site. What it did is it provided a unique opportunity to test a new technology that's not being used in Canada, but it's probably very common. It is very common in Europe and elsewhere in the world, but we haven't used it in Canada yet. In red, first of all, is the third GPS, where we have the 55 millimeters a year of movement. Tracks to the north, tracks to the south. Well, we have this great retaining wall here, and there's one of our corner reflectors. This area here is where we did the last transect. This is where we have the maximum amount of movement. So we're using this retaining wall here to test a new technology. And that's fiber optic technology. Here's our colleagues from the China Geological Survey installing it. This is the instrumentation in the bungalow. This is the application of the fiber optic cable along the retaining wall, and you can see already a bit of a deformation since the retaining wall was actually put in. And this shows the configuration. We essentially gridded it entire system there with over a kilometer worth of cabling to make sure we got a good two-dimensional signature of what's moving. And then these are the trigger points of what's actually moving. So here's some of the results of our work to date, and we've got a number of peak areas along here. This is for the BOTDR that's consistently showing excessive amounts of noise throughout our first 6 months of monitoring. So we're quite excited about adopting this new technology at this particular site, and of course we'd like to start using this elsewhere in Canada if it proves successful. Sorry, I've only got 30 seconds left. But here's a unique type of hazard that we have at this particular site. Those of you that haven't worked in Canada, it's actually not a hazard to us, because while we're working there, you actually don't see any wildlife at all. But we are in a grizzly area, and ironically, first of all, I'm going to show you, if you've never seen one of these creatures, of course, you know what type of claws they have. Well, we were starting to get instrumentation problems, so we went back to the site, because as I said, we can do remote downloads, and we lost the signal. So when I went back to the site, this is what we saw, and you can see the actual claw marks on this. Most of our cabling that was polyfilled in like this was destroyed by bears because they didn't know what it was, so they sort of pawed at it, maybe chewed at it, and then left. Unfortunately, this cost us a lot of money. So in hindsight, of course, we didn't know that this would attract. We thought we were protecting the cabling from squirrels, small animals, but what it did was it attracted these large predators. So lesson learned for us, we probably should have just left things as is and nothing would have happened. And now it's too late essentially to remove all of this polyfilla. So basically in summary, first of all, we've got these 3 GPS stations. They've noted deformation up to 55 millimeters a year. Inclinometers were installed, but as I said, they were quickly sheared off. There have been 2 drill holes. We hope to do 1 more drill hole down to a depth of 30 meters, which is well into bedrock. We've also we've taken samples from the drill holes. We're going to do Atterberg limits, shear strength. Those properties are already collected. 9 corner reflectors have proved extremely useful. This is a technology that's now going to be used by the rail companies elsewhere. We've also done shape accelerate, piezometers. We've done ground penetrating radar, electrical resistivity, etc. And as I said, we're extremely happy to be the first location to be testing, in collaboration with these other methods, the fiber optic technology. So we're planning a lot more instrumentation. We're constantly trying to adopt new technology to the site to really make it the most monitored site in Canada, and other plans for the future to help minimize the impact for these rail companies that we could help out with. So thank you very much.
Thank you, Peter.